that actually it is not simply one index, but you could be breaking it down into different types of indices depending on how spatially and temporally this phenomenon is evolving. But its linkages with both the monsoon in India, in Africa, in Australia, and so on, it's been well established. More recently, in 1999, another driver of the Indian monsoon was discovered by Saji et al. And this is the Indian Ocean Dipole. So very crudely put, there's a pileup of warm waters in the western Indian Ocean influences rainfall over India. And then if you have cooler waters piling up and warmer waters further eastward, then you have the other part of the dipole. So that's why it's called a dipole. Furthermore, there has been over the past few decades increasing evidence that there is a trend in extreme rain events over India over the past century, or at least over the past few decades. And in I think just a few years ago, about 975 millimeters of rainfall fell in Mumbai, and it had caused a lot of devastation. And there are reports from other parts of the country as well in terms of higher uncertainty, both spatially and temporally in rainfall, as well as increased prevalence of these so-called extreme rain events. In our current project, our objective is to understand the spatio-temporal dimensions of what is an extreme rain event and the hydrologic and carbon response to these extreme rain events, because they can completely change the moisture regime. And depending on whether you're in an urban environment or a forested environment or a different type of agro-ecosystem, what constitutes an extreme event, both in terms of the rainfall process as well as the response to that rainfall process, is something that's part of the larger project. But what I will be dwelling on today is basically what is the dynamic and evolving influence of these two drivers, known drivers, the Southern Oscillation Index and the Indian Ocean Dipole on the Indian monsoon, and then what are their relative roles in terms of the frequency of extreme rain events in India. So what do we find? Are they the drivers of extreme rain events? Because there's been a lot of work done, other work which has been done, which talks about the influences of global warming on the acceleration of the hydrologic cycle and turnover times, and also other regional and global influences, including things like aerosols and also a lot of complicated processes operating. Some are negative, some are positive, and it's not very clear what actually are the drivers of these extreme rain events, and that is the motivation behind our work. Using secondary available data, we also have instrumented catchments throughout the Western Ghats in the works, and so we're going to combine data from the ground and our insights that we gain from secondary data to build a much better picture of the spatio-temporal dimensions of extreme rain events and their hydrologic and carbon responses. So the dynamic linear model has already been introduced by Professor Gaur earlier, so I just mentioned. It's simply you have a response variable which varies in time, yt. It could be the Indian monsoon, and it's a function of unobserved state variables, theta t. It could be simply a trend component. It could have a cyclic component, or it could be thetas could be the regression coefficients of where you have regression variables such as the Indian Ocean Dipole or the Southern Oscillation Index and so on. And then the coefficients themselves, they perform a random walk about their previous state, and the observation variance Vt and the system evolution variance Wt, they are important parts of defining this dynamic model. And if you take the ratio of Wt to Vt, that would actually be equivalent to the equivalence of signal to noise ratio. And so that's something that you have to fix as you have to come to some understanding of what values that you want to fix for that. Observation variance itself you can get by, for example, assuming a static model, and you can get your observation variance from an ordinary regression model, for example, or by maximum likelihood estimates. And since these are the starting points, and this is going to be a dynamic system, actually the starting values that you, except for the signal to noise ratio, which doesn't change through the evolution of the time series, the influence of the initial prior distribution for your parameters had some influence in the beginning, but over a period of time that influence wanes. And periodically at each state, at each point in time, the prior distribution which is available is used along with the data and the model to compute a likelihood, and you can update the probability distributions for your regression coefficients. So at each time step there's an updating, and if there's missing data, well, the prior continues, so it can allow for that. And so it's a combination of the Kalman filter, because if you're working in the one step ahead forecast mode, then the departure of your forecast from the actual observed value will feed back into the system to help correct the state of the system, that is theta t's, and then you have a different estimate. And so that's how the regression parameters can evolve through time. And so this is a regression framework. So you would have a time varying intercept, you will have a time varying slope, and you can have two slopes depending if you have like two covariates. And so what you really have is that in a static regression, the intercept and the slope are invariant, in the sense that all the data goes into estimating one value of the slope along with uncertainty about that, as well as one value for the intercept with uncertainty about that. Here what we have is an estimate of the intercept and the slope at each point in time, along with their uncertainty as expressed in Bayesian credible intervals. And then the assuming conditional independence and this recursive nature, so you can condition it on the data observed up to a particular time and make a forecast for the next time step. And then if you're interested in what happened in time rather than using it in the forecast mode, you can condition it on all the data that has been observed even after a particular time t, in which case what you will have is a retrospective estimate of the state variables conditional on all the data that's been observed. So this is what we have, since we are interested in a retrospective analysis of how did the relationship between the Indian Ocean dipole or the Southern Oscillation Index and the Indian monsoon evolved through time over the last 100 odd years. So what we really are using is a smoothing distribution at time t, which uses, as I said, the data that's been observed even after a particular the time corresponding to the particular state. And so in order to initiate the DLM, you need some prior estimates to begin with. Your prior estimate for your intercept, for your regression slope, or if in case you are not working a regression framework, you might be interested in having a time series decomposed into a trend component and a seasonal oscillatory component, in which case you need to have some prior estimates for those parameters. So in the case of regression, one simple way that's been used, I've used this in the past and others have used it as well, is that you can use part of the data in the beginning. If you don't know anything about the system, you can use part of the data in the beginning to fit a model and then use that as initial priors, or you can so that consumes some amount of data, because that data then can't contribute to the actual analysis. So it depends on how much length of time series you have. The other approach is that you assume null condition, you assume static conditions where the regression coefficients are invariant. So you're basically fitting an ordinary regression model, and you can use that the intercept and the slope that you get and the variances associated with that as an initial starting point. So I'm not going to repeat this because a lot of this has already been mentioned by Professor Gore and others in terms of the dynamics of this, how this modeling, including the Kalman filter. So here there are some issues and assumptions that are worth considering. The time variance of the observation variance and the system evolution variance W. So that's one important assumption that we make. It considerably simplifies, because unless you have information to suggest that the observation variance or the system evolution variance has changed through time, then typically what we assume that V and W are invariant during the course of the study period. And the estimate of the observation variance can be obtained by fitting a static regression model, which assumes the invariance of regression parameters with respect to time. And then you have to make a choice about the ratio of W to V, which is your signal to noise ratio. And that's the little tricky part. If you want to be conservative, you can fix it at something like 0.1 or something, unless you have information to suggest that the it can be different. And the other thing is that this W is actually a matrix, and so you have the values of W for each of the parameters that are in your model. So your intercept can evolve at a certain rate, your slopes can evolve at a different rate. I have typically in the past and recently have, in the absence of any other information, kept them the same. So basically what you're saying is that the rate of response of, say, the Indian monsoon to either the IOD or the SOI, we are assuming that that is going to be similar, and that can be contested depending on the information that you have. And then of course the initial price that I've already talked about. Either you use a little part of the time series in the beginning if you can afford to do that, or you can fit a static model, or in some situations in biological or ecological phenomena, you might actually have a previous study available which has already established certain values of these parameters along with the uncertainty, and that you can feed into your initial priors. So what we have here is this is just the Southern Oscillation Index and the Indian Ocean Dipole indices after removing their dominant periodicities and plotted from 1901 up to 2000. And after removing the principal periodicities, you can see that the Indian Ocean Dipole seems to be showing a rising trend, and the Southern Oscillation Index had a lot of variability, but in more recent decades it seems to be showing somewhat of a downward trend. And then when you plot these two together, you can see that that relationship between the two, while on one hand it suggests that they may have some correlation between them, but it also suggests features that are independent. So it's a little complex of what is the actual relationship of the IOD as part of this overall oscillation. So this is the model, which is the monsoon at time t as a function of the Southern Oscillation Index and the Indian Ocean Dipole. So this is a dynamic model. So your intercept is AT, your slope B1t and B2t, and these evolve through time. And what we have done is we have conditioned it on all the data that's been collected. So what you have here, the second part, the second graph, the second column is the monsoon ENSO slope, and the third one is the monsoon IOD slope. And what's left over in the intercept is basically other sources of variability that are unaccounted for in your model. Your model itself is of course a simplification of a very complex system in any case, and so there's going to be a lot of variability that's going to creep into your intercept. And then what we have here are the 25th and the 75th percentile Bayesian credible intervals. You can choose any other, but in a system as uncertain as this, if you try to have a 95% credible interval, you're not really, you won't be able to even be able to look at the dynamics. But what we can see from here is that the Indian Ocean Dipole slope with respect to the monsoon seems to be showing a rising trend. So that is, the strength of the relationship between the Indian Ocean Dipole and the monsoon does show an increasing trend. And if you compare that to the monsoon SOI slope, that shows a lot of variability, and then in more recent decades there's a bit of a decrease there showing. And other work has also shown the so-called waning influence of the Southern Oscillation Index with the monsoon and so on. So it's a pretty complicated picture, but what emerges clearly from this dynamic model is that the strength of the monsoon IOD relationship, that's the third plot, is showing a rising trend. And then when we actually compare, for example, how good the dynamic model was with the actual observations and compared to the static model, the static model assumes that the regression, intercept and slopes are invariant with time, whereas in the dynamic model on the left hand side, you have time varying evolution of the regression slopes. And we can see that the dynamic model has done a much better job of predicting the monsoon totals overall compared to what we see is a very, very noisy relationship on the right hand side. So I think that there is some merit in considering these dynamic models in monsoon forecasting and prediction. So then the second part of the work which is related to actual high intensity rain events, because that's something that we're really worried about, and this project is about studying the effects of extreme rain events and the hydrological and ecological responses. So yeah, okay. So I'm not going to introduce the Poisson regression, the generalized linear model. It's already been introduced. since the number of extreme rain events in a particular year is a count variable, and you can use a Poisson regression. So I ran two types of a generalized linear model, or assuming Poisson distribution. One was with respect to time, and the other one was with respect to the Southern Oscillation Index and the Indian Ocean Dipole. So what we see is that if you look at rain events exceeding 50 millimeters a day, or rain events exceeding 100 millimeters a day, 200 millimeters a day, or 300 millimeters a day, or 400 millimeters a day, we generally see an increase in the frequency of these events over time, and not only that, we also see an increase in the variability, spatiotemporal variability. So this analysis is based on 73 stations spread over India, and what on the right hand side of each of the Poisson regression and the scatter plot, what we see is the locations of where these high intensity rain events occur. So we are seeing a signal of increased variability associated with these high intensity rain events, and all the trends were, of course, in the frequentist sense, they were all significant and so on, but nevertheless, I think even without fitting a model, I think that one would be able to, simply by looking at the scatter plot, be able to come to the conclusion that there does seem to be greater prevalence of such events over the last century or so. And when we actually look at the coefficients from the Poisson regression, we find that as the rain intensity increases, the slopes with respect to both the Southern Oscillation Index as well as the IOD are increasing, and when we look at the error bars and so on, and this is a model in which both of them were covariates, the Southern Oscillation Index as well as the Indian Ocean Dipole. And the Indian Ocean Dipole has smaller error bars and is more it seems to have a stronger relationship with the ability to predict high intensity rains. And when we actually look at the coefficients and the standard errors and the p-values for the models in which both covariates are included or they were included individually, we actually find that the Indian Ocean Dipole seems to be having a stronger ability to predict the frequency of high intensity rains. Then if you want to, that was a generalized linear model, so it's a linear sort of a system. You can also use generalized additive models in which a smooth function is used instead of linear, and so that's how it is. It's basically the same type of information, but you can pick up the non-linearity in the relationship between the response and your covariates. And what we see is that the 50 millimeters rain events exceeding 50 millimeters a day, 100, 200, 300, 400. You see that the Southern Oscillation Index, so that's the first column, has some sort of a threshold, and there's a lot of high variability associated, and then it doesn't seem to have a monotonic relationship at all with respect to the response variable. Whereas on the second panel, which is the Indian Ocean Dipole covariate, you can see that as the Indian Ocean Dipole values are increasing, there is a higher frequency of rain events in each of those categories, consistently from 50 millimeters a day all the way almost up to 400 millimeters a day. So there's definitely a very complex situation here. First of all, the relationship between the Indian Ocean Dipole and the Southern Oscillation Index itself is an area of inquiry. There have been speculation about whether it's an independent event and how it's linked and so on. And so in that sense, this is a very approximate, we are treating each of these as covariates, independent covariates, so there's a lot of assumptions going on here. But nevertheless, in spite of all these uncertainties about assumptions and about the process itself, we are nevertheless seeing a very clear signal that the Indian Ocean Dipole may have a lot to do with the prevalence of high intensity rains, and is something that we need to take a closer look at. So these are some of the resources. The dynamic linear model, now there's an R package, you can pick up functions from that and write your own code. And there's an earlier version, the Bayesian analysis of time series, produced by Mike West at Duke University. Now that was written for Windows 95 or something, and nowadays it doesn't even run on all the modern Windows version. So, and that's sort of a very black boxy thing, you can't really change a whole lot of things in it. Whereas with the R package, you can write your own code, you can pick up functions, you can build in a annual cycle as part, an oscillatory component as part of your You can mix and match. What it doesn't have is, of course, it's all of the functions currently available in the DLM package by Giovanni Petris are all based on Gaussian assumptions. So if you are looking at, for example, Poisson distributed, like counts and so on, and how that changes with time and those sort of. So there's no generalized linear model equivalent of the DLM in this particular package, but there is work which has been done elsewhere, and those are available also. And these are just examples of paper. I've used dynamic linear models for modeling sedimentation changes in river basins over multiple decades. And then, in fact, Rajiv and Nagesh, they used the similar DLM to look at monthly Indian summer monsoon. And again, they looked at ENSO and the Indian Ocean Dipole. So it's already being used, but I'm not aware of whether for a monsoon forecasting, what type of dynamics have been included in the forecast that currently operates in India. I think Professor Vinod Gaur will probably be able to comment on that more. But I feel that dynamic models may perhaps even develop for regional separately for cyclonic or for other parts in spatio-temporally. We can disaggregate and break up this aggregate Indian monsoon into different components and try to have a dynamic model for forecasting. I think there is some opportunity there. So in essence, these Bayesian dynamic models, they offer a lot of opportunities to study dynamics of very complex hydroclimatic and ecological systems. And of course, generalized linear models, and especially the generalized additive models, are very useful in studying non-Gaussian and non-linear relationships, and at least in terms of an exploratory phase. So that's about it. I think I left some time for.
Yes, definitely. So thank you very much, Jagdish. As I said, there are several minutes for questions.
So did you try this on the seasonal total rainfall as opposed to the extremes?
Which one?
The same method.
See, the dynamics that I showed was only for the total summer monsoon.
Right, but then you looked at
the second part of it, where I looked at the extreme rain events, there I have not yet used the dynamic model, except for that Poisson regression with respect to time.
So just looking at the number of events
per each year and so on. And actually, one could have a Bayesian approach to that. You could have, for example, if you expect that the number of rain events per year is going to increase over time, if that's informed a priori, one could have had an a priori probability distribution for that parameter. And then one could get a Bayesian predictable interval using a generalized linear model approach. So that can be done. But sometimes if you don't know whether it's actually increasing or decreasing with respect to time, then you may want to have an uninformed sort of but I think there is enough information to suggest that these events have been increasing. And so if one had to do a Bayesian equivalent of the generalized linear model, one should definitely use an informed prior for the parameter with respect to time. And even the relationship between the Indian monsoon and the Southern Oscillation Index and the IOD is fairly well characterized. So if you expect a positive slope, then one can have a prior distribution to encompass that. And if you expect a negative slope, then you can have a informed prior distribution for that as well. So in that sense, I think that it is something that we can do. And also looking at the monthly time series, that would definitely be the next logical thing to do.
More questions?
Professor Gaur, any comments on the monsoon forecasting?
Okay, so let's thank Jagdish again, and